And I haven't worked it out, so I'm not 100% sure that we end up with m equal 1 minus n. So you want to check me out on that. Okay, so I'll just kind of circle that and circle this. I'm 99% sure of that, but my level of certainty is exponentially decreasing with age. So double check it. Okay, well that's your Bernoulli equation. Other substitutions, and I'm actually going to cheat just a little bit. There's one that I'm not thinking of. Okay, I don't want to write that one out. You can look up the homogeneous equation, but and I'm just looking for notation here. They're using the m and n notation here, so I don't want to confuse you by using a different notation. They use the m on the dx and the n on the dy. Pretty sure that one reason I get confused about that is some authors do it one way and some the other. But maybe I'm just confused. Okay, and either way it's okay. Okay, but if you have, okay, homogeneous, of degree, we're supposed to be degree, and I have no idea where the h came from. Hopefully that won't smudge too bad. I've always used n for the degree. Your book uses alpha. And it again. Shucks. Sorry. Okay, m of tx ty gives you an expression that you can factor t to the alpha, out of which you can factor t to the alpha, leaving no more t's within the function. That's what it amounts to. Then this function is homogeneous of degree alpha if and only if m and n both homogeneous of degree alpha. In which case, let me make sure I write it down right. Yeah. If that's the case, the change of variables u equals x over y, v equals y over x makes the equation separable. Okay, well, that's your homogeneous equation. You also have the linear equation, which we addressed. If your function is, if you have like a y prime equals f of a linear function, then you have a straightforward conversion. Let me just find that and put this in the, well, I don't see it. This thing's jumping around on me. Initial value problem, and that's the end. Well, anyhow, it's y equals f of some linear function. Okay, then you just let u equal the linear function and it becomes tractable. Okay. Now I don't see the notation your book uses, but that's pretty much an overview of your first order equations, except for your numerical method, which is just your simple Euler method. And I'll review that because it's important also for understanding your existence theorems. Okay, and maybe a quick mention of that. So if you have y prime equals f of x, y of a equals b, and you can't solve this, none of your methods work. Okay? And there are plenty of equations where nothing is going to work. Okay? If this isn't integrable, you're probably out of luck, in a certain sense. Okay, and that gets a little deeper than we want to go, a little deeper than I want to go. I can't characterize what's integrable and what isn't. Not sure it can even be done. Okay, so you put the picture of this in the plane, and you have your point A, B. And we could call that, if you want, x naught, y naught. You calculate the slope here. This gives you a way to always calculate the slope. Okay, so first of all, okay, this allows us to calculate the slope at any point. And now it tells me I got 61 minutes of camera left. Okay. Okay. Get a little nervous. Don't want to lose that just in case this is messed up on Zoom. Anyhow, that allows us to calculate the slope at any point. So we can calculate the slope. So we calculate the slope and we draw a little line segment. I'm going to draw a big line segment, but you want to think in terms of a tiny one. You calculate the slope. And I'll use x naught, y naught. I could use a and b, but I'll use x naught, y naught. And you then specify some increment h. Now when you first use this thing, h is always going to be the same, but there are a lot of cases where just the behavior of the slope dictates that some places you want to use a smaller value of h. Some cases you can get away with a bigger value. But right now I'll just say you got some h, and we'll just use the same h everywhere. Then what you get is you get a rise a delta y equals the slope multiplied by h, which is of course f of x naught y naught times h, giving you a new point. Looking for a good color to use. You know, better start my last piece of purple chalk here. Okay, and that gives you the point here. That we'll call x1, y1, and it should be clear from the geometry here that your x1, y1 is this. Now this is a formula you can use mindlessly without even seeing what goes on here. Okay? I don't recommend that the formula be used mindlessly. And of course, if I ask you a question about this on the exam, I want to see mind. Okay? I don't want to see mindless application of a formula, which I think is so unnecessary for any competent student who's doing this. The formula's not that hard to remember, but it's much easier to just understand this picture and apply it. And then it becomes obvious that x2, y2 is going to do the same thing from the point x1, y1. Okay, and you could draw the picture here, and we did the picture in quite a bit of detail. And this is what's going to result. I'm not going to explain it. And then, in general, xn plus 1, yn plus 1 equals xn plus h, yn plus f of xn, yn times h. And then you can move on as far as you want. Now, as you move through this process, you have, I'm going to try my red chalk here. Oh, excuse me, the floor's a long ways away. I've been standing so long. Okay, got through that without injury, so I'm good. As you go through this process, you tend to have accumulating errors. And it's in analyzing these errors and the values of h that you need to get a reasonably accurate solution, whatever reasonably accurate might be in a given case. You want to keep these errors within bounds. You can also is there a color I haven't used here? There ought to be another one. Yeah, I'll just do it in red. Okay. Just a couple of other notes. So to start getting a handle on these errors, which increase along with the slopes. The greater the second derivative, the greater the rate of change of your slope, the more error you make by assuming the slope is constant from here to here. And that's what you're assuming every time you do this. You minimize that error by making h small enough, but the smaller you make h, the more error you get, the more computation you need. And that extends to astrophysical simulations, simulations of emergent properties in magnetic fields. And I talk like I know, well, I do kind of know how those things are approached. But the details, you know, I'm not so specialist in those. I'm not even a good amateur in those areas. Okay, anyhow, you compare your solutions with actual exact solutions were possible. And that's the kind of problem you can sort of expect, where I kind of probe for a little bit of insight into the process. Means you know, a lot of times I give you an equation that you can easily solve, but ask you to do this approximation and see how the approximation deviates from the exact solution. That's very important because in some areas the equations that you get are never solvable, or very seldom solvable, but they're very important. Okay, so you can do that. Another thing is, a solution can't cross a point where solution is not defined. Perhaps because it doesn't exist, perhaps because the function f of x, y no longer applies to your situation past a certain point. And this is key to some of your existence theorems, okay, where your general function can't be solved if any of the coefficient functions are undefined. It can only be solved within an interval where your coefficient functions are defined. Well, that's kind of the end of what I hope to say, and it's kind of just a few seconds from the official end of class time. Not that I'm in a hurry, but I know you've got a schedule. So I'm going to cut it off there. Do you have any questions on any of that or anything else you'd like me to address? I would be willing to make you know, additional videos on specific questions or specific areas.
I don't think so. That was super helpful, though. Thank you.
Yeah, well, that's an overview, so refine it.
Yeah.
You know, make sure you can get down to the details that actually apply when you get your hands on a problem. Okay? So,
okay.
If that's it, if there's nothing else, I'll let you go. But I'm not in a big hurry. So give everybody my regards.
I will. I've got a few April Fool's pranks that I got the ball rolling right before I left, and I want to see if they've come to fruition yet. So.
Oh, good. Fill me in next time. I'd be interested to see.
I will.
How some of the reactions are, especially if they apply to some of the people I know. But yeah. Either way. Okay. Well, have a good rest of your day, Richard.
You too. Bye.
Bye-bye.
Recording stopped.
Okay. You know, on these camcorder videos, I might get tired of seeing my hand. You know, first time I saw this, I didn't know what in the heck I was looking at. Kind of scary, some kind of creature from wherever, or some kind of microscopic thing. So I'm going to do a merciful thing here and see how this works.